Okay, let's get back into things. So, after having your mind blown, let's try to take a breather of sorts. Let's try to go back a little bit. So, let's try to assess where we are in the class now. So, what have we done so far? Yeah, we talked about regular languages, right? So we talked about a whole sort of languages. So we talked about what types of things did we associate with regular languages, though.
DFAs, NFAs,
Yeah.
GFAs,
Yeah, perfect. So DFAs and NFAs. So those were the machine model, right? Well, GNFA too. So DFAs and NFAs were the machine model for the regular languages. So then what did we talk about right after that? Regular expressions. Why did we talk about regexes? Because I want to torture you guys?
English side.
Well, part of it is that. What was it?
We simplify. We simplify the NFAs.
No, because we're going. That was the transformation from a NFA to a regex. Well, so why are we considering the regexes in the first place? Yeah. What is more specific? Right. So we had this weird issue where if we wrote the language out in English, it was hard to interpret what exactly the language was. So by looking at a formal way of writing out the language as a string, which is the regex, we looked at that and we saw, oh, they're the same as regular languages because we can convert back and forth between NFAs and regexes. Cool. So let's talk about another way to actually get the regular languages. So the reason we're going to actually touch on this is that it generalizes well to the next big topic that we're going to get to. So instead of talking about a machine model for regular languages or a way of describing the regular languages, what if you have a regular language in mind, and you tell me a list of rules that you could apply to get strings in the language? So what about generating the regular languages? So if you haven't heard of this, this is something called a grammar. So how many of you have taken 340 or are taking it right now? Yeah, so 340, you're going to be very intimate with grammars. So we're only going to briefly touch on one type of grammar before we launch into the grammar that's used in 340. So let's see. Suppose that we wanted to generate the language 0 star. So a very simple language. Well, let's see. What is one string that you can guarantee is in this language, our favorite string? The empty string. So one way we can say is, I'm going to allow you a rule to say, you can generate the empty string, okay? What about a non-empty string? Well, if we have a non-empty string in this language, it's a bunch of zeros, of course. Well, let's see. What do we know about this piece right here? Ignore the front 0, just the stuff on the end. What do we know about that string of zeros? Is it also in this language? Yeah. So we need to be able to say, oh, you can generate this character 0, and then after you do that, generate another string from the language. Okay? Because that's all this string is. Well, we know that if you have a 0 on the front, I can make a string that has even more zeros in it. I don't necessarily have to generate certain strings of zeros. I can generate anything with a 0 on the front and anything afterward. So here's how we're going to write this. We're going to say, well, we're going to start at S right here. And the way we're going to write the rule is you can generate the empty string, which is the first thing we talked about. And we're going to denote that by an arrow with an epsilon. So the thing on the right is the thing you can generate. I'll talk about what the terminology of each of these things is, but this is the way we're going to say you can generate something from a start that we're going to call S. And we notice that for a longer string, we can write that as a single 0 followed by something that we can restart at S again. So the string without the front 0, that could also be generated by S. So another rule that we want to add here is S can generate a single 0 followed by S. So this thing right here is called a grammar. So a grammar has these rules that you can generate stuff. And how do you know when you're done? You're done when there's no S left in the thing that you've generated. So let's try to generate 0, 0, 0. So the place that, that's what we want to generate. So the place where we have to start all the time is the S here. So we start at S, and I'm going to explain this notation in a second, but we're going to use one rule application. So which of the two rules should I apply if I am destined to get 0, 0, 0? The second one, right? Because the first one, if I apply that, then there's no S left. So therefore, I can't apply any rules after that again. So I better apply the second rule to get 0S. And one more thing is, when you generate a character like this, the 0 that's generated, it'll never be deleted. So that when that 0 is generated, it is done generating for that 0. But we can go into the S again because there's still an S here. What rule should I apply again?
Second one.
Second one again, and we're going to get 0, 0, S as a result. And then we can see we should apply this second rule a third time to get 0, 0, 0, S. But now which rule should I apply if I want to get 3 zeros?
The first one.
The first one, obviously, which means that the S will be replaced by epsilon. So it's going to be replaced by epsilon, meaning I get 0, 0, 0 at the end. And since there is no S on what we just generated, we're done making the string. So this whole process right here is called a derivation. So all a derivation actually is you start with S, you apply rules over and over and over, and then you eventually get a string with no S in it. Fair enough? Okay, so that statement's not actually correct because we can have other things on the left side of these rules, but does that example actually make sense so far? Okay, so let's actually talk about a grammar for regular languages. Oh, by the way, so notice, how many characters in each of these rule applications am I generating? Of the final string that I want. How many characters am I generating every time? 1. How many characters can you read on a transition on an NFA? 1 or 0 for epsilon. Do you think there's a coincidence? No. So we're going to restrict the rule types to here to say you can only generate 1 character or 0 characters. Okay? So that it turns out if you make that restriction, then it coincides with regular languages. So a regular grammar then is a 4-tuple. So for DFAs and NFAs, it was a 5-tuple. This time it's a 4-tuple. And here they're going to have different names other than one of them. So V, sigma, so our friend sigma is back again. Sigma's back again. Anyone remember that song? Yeah. All right. So R and S. So the 4-tuple has V, sigma, R, and S. So what are these? So V is a finite, so everything's finite here. Finite set of what are called variables. If you've taken 340, you may see the term non-terminals, but we're going to use the term variables here. It kind of is weird to define something as not something else, but I guess that's the notation they use. Sigma then, because they're called non-terminals sometimes, sigma is a finite set of terminals. We'll talk about R in a second. S is a member of V. So just like with DFAs and NFAs, Q0 was an element of the set of states. Here, S is an element of the set of variables. So it's the same idea. And we're going to call this is the start variable. And R is a finite set of rules of the following forms. Actually, following 4 forms. So there are only 4 types of rules that you can have. You can have as many of them as you want, as long as it's a finite number. But there are only 4 categories of rules that you're allowed to have here. So so let's actually think about what types of rules do we want. Well, if we want these to have the regular languages, okay, they're destined for the regular languages. What string must be should we be able to generate always? Yeah, empty string. So we're going to allow you to have a rule type that has A goes to empty, where A is a start variable. Is a variable. So that's one rule type you're allowed to have. Any variable can make the empty string. All of them could, or just one, or none, or anything you want. What other strings do we want to get? Well, if it's not just a string with no characters, what about the strings with 1 character? Should we be able to get those? Yeah, because those are in the regular languages, so we better get those strings too. So I'm going to allow you to go from a variable to a single terminal. So I'm saying little a here is a terminal. So a is a variable, little a is a terminal. A is a variable, little a is a terminal. Well, let's just say, for sake of argument, that I forced you to only have these 2 rules. These are the only 2 rules types you're allowed to have. Could we get all the regular languages? No, why not? Well, yeah, so if we are at the start variable, whatever rule we apply, if we're restricted to these 2, we can only get the empty string or a string with a single character. So therefore, we can never get a string with 2 characters in it. So we better have some way of going from a variable to some other variable if we want to be able to get longer strings. Well, we're going to have the other two rule types be you can immediately either go to another variable without generating anything, or you can generate one terminal and go to the other variable. So the way we have that is A can go to B directly. So A and B are both variables. Or we can have A goes to little a with a capital B, where A and B, of course, are variables. Little a is a terminal, just like before. And these are the four rule types I'm going to allow you to have. So take a note here. The terminal is on the left side of the variable. So it'll turn out to be equivalent if I said, I'm forcing you to put it on the right side of the terminal. Right side of the variable. So instead of AB, I could have BA. As long as we're consistent, we're okay. It turns out, if I allow you to have AB and BA, we can get non-regular languages. So it's very important that we only have these rule types, because if I add any others, we could get non-regular languages here. Okay? Any questions on just the definition of this? Well, let's see. If these things are destined to have the regular languages, what do we need to show? If these things could generate the regular languages, what should we show? Yeah, so if we can convert a regular grammar into a DFA, and the other way around, from a DFA into a regular grammar, is that enough?
Yes.
Yeah, because this is not our first rodeo, right? We've done this before. We've been here. We did the same thing with regexes. We went back and forth between an NFA and a regex. Is it okay if I use an NFA here?
Yes.
Yeah, why?
They're equivalent.
Yeah, because DFAs and NFAs are equivalent. We've seen that before. So an example we could have is S goes to 0A and A goes to 1S or epsilon. So that's just an example regular grammar that we could have. So this, here's a notation that I haven't talked about yet. That vertical bar means another rule. It's just shorthand. So it's saying that A could generate 1S or A could generate the empty string. It's just two rules that are written together. It's not like anything else. It's this rule or this rule. Okay, but notice, in all the four types, what is on the left side? A variable is always on the left side. And also note, it's just a single variable and nothing else. It's not two variables, there's no terminal there. It's just a single variable, which is pretty interesting. Well, from an NFA's perspective, how do I know what transition to pick? So what things do I need to look up for the transition function for what transition to pick? Current state and the symbol. So do I need to know any other state at all? No, I just need to know that state and the symbol that I want to read, or in the case of NFA, not read. Well, let's see. Could we make an NFA out of this? So the question is, could we transform a regular grammar into an NFA? Or DFA, but NFA will make this a lot easier. Well, let's see. What if, think of these arrows right here. So like, think of the rule types 3 and 4 that go from one variable to potentially another. Notice here, those kind of look like transitions between states. Well, let's see. In the case of the third rule type, which is the A goes to B rule, if I had a transition from a state A to a state B, what would that look like on the transition itself? Am I generating anything here? No. So should we read anything off the input here?
No.
No. So what should the transition be?
Epsilon.
Epsilon. Okay, cool. So we can actually view this as grammars could generate the string we want, and NFAs are reading the string that we want to determine whether it's in the language. Well, what about the fourth rule type? A goes to AB. So remember, is the generated character A here, the little a right here, is that ever going to be deleted? No, because no matter what happens, when I generate that, I can only take a variable and replace it by something else. I can't take a terminal and a variable and replace both of them simultaneously. I can only replace a single variable. So once the character is generated, it's there forever. Okay, well, think about the NFA's perspective. If I read a character, am I going to ever see that character again? Think there's a coincidence between those two? No. So in fact, what do you think is going to be on the transition between these two? A. Because we're reading the character off the input, but correspondingly for the grammar, we're generating that character. Oh, pretty cool. Oh, 2 rule types done. We're on the right track to get the other 2. So let's do the other 2. Let's do the first rule type. A goes to epsilon. Well, is there a variable on the right side? Wait, so if we were thinking of variables in the grammar as states in the NFA, this can't work now. Right? Because there's no variable on the right side of this rule, so I can't make a transition to a state if there is no state, right? Oh, hold on a second. Hold on to your hats a second. Think about using a grammar like this, okay? So we're using this grammar. So I apply a rule, apply a rule, apply a rule, apply a rule. How many variables do I start with? The very beginning. The first thing that we do, how many variables we got? 1, which is which one? The start variable s. If I apply a rule, could I ever go to 2 variables that appear at a certain point? So if I apply a rule with 1 variable, could I get 2 variables? No. Think about the rule types. Look at the last 2. I'm replacing A, the variable A, with a variable B, or the terminal with the variable. So whenever I have a variable, 1 variable, I'm replacing it with another one. Or a terminal, as the case may be. But could I ever at any point have 2 variables or more? I start with 1, I replace it with another variable. Could I get 2 variables? No. I can never have 2 or more variables because I'm just replacing one with another. And there's no rule type allowed here that has 2 variables on the right side. So I can't replace 1 to get 2. Well, could we have a situation where we had 1 variable and then after we had 0? Yeah, well, what cases correspond to those? Which ones? 1 through 4, which ones? We go from 1 to 0. Rule type 1 and 2. Okay, cool. So, let's see. So, no matter what happens, we are either at one variable existing or 0. If we have 0 variables existing, can I apply any other rule? No, because remember, we're replacing a variable with something. Okay, so if I have no variables appearing, I can't replace anything. So that means that the computation in the NFA is done, quote unquote. So however we're going to handle this, the first 2 rule types, we better do something special. Okay, but furthermore, if we apply one of the first 2 rule types, we're done the computation, right? We can't generate anything else, correct? Can we generate anything else if we have no variables to work with? No. So, what about the NFA? Should we be in a final state if we apply one of those 2 rule types? If we're done generating things for the grammar, that corresponds to being done reading things in the NFA. So if we're done reading things in the NFA, should we be accepting? Yes. So no matter what we do with the A to epsilon and the A goes to little a rule, those should go to a final state. But should I make any of the variables a final state? The states corresponding to variables be final? No, because then I could be generating other things, and then I might not actually be done. So we better make a brand new final state as a result. So let's make a new final state, and I'm going to call it F for final state, and make that final. And then naturally the transitions are epsilon and little a on these. I'll do an example in a bit. But any questions on why we're doing it this way? Okay, so let's see. Let's do this example. Let's copy it down here. Okay, so how many variables are in this grammar? 2. And those are S and A. Where did you look to find those? On the left side of the rules. Cool. Which one's the start variable? That was very emphatic, but are you sure? Could it be A? If I wanted it to. Could I? Yes. So unless I tell you, you can't assume just because the variable is called S, that doesn't necessarily mean it's the start variable. But in here, we're going to call it the start variable. Just to make it easy. Okay, well, let's see. If we're going to be making variables for the states, states for the variables in the grammar, how many states are we going to make just for the variables then? 2, which are S and A. How many states in total are we going to make? 3. What's the third one? The new final state. Cool. And the variable states are not final also. So SA, and then that new final state called F. So what are the transitions in this grammar looking like? So let's handle the S goes to 0A rule. How would I make that as a transition in the NFA? Yeah, read a 0, go to A. Yep. What else? What about the A goes to 1S rule? A goes to 1S. Read a 1. So it's the character that we read along the way. I probably shouldn't have done 1 because it kind of looks like a vertical bar. Yeah. Yeah, let's switch it up. Yeah, I noticed that just now. Let's make it little a and B. So then the 0 becomes an A, and the second one becomes a B. Okay, are those all the transitions? No, what's the other transition? Yeah, epsilon transition from A to the final state. So think about what happens here. Suppose we generated the string, wanted to generate the string AB. Well, how would we do it in the grammar? Well, where do we start always? Yeah, start variable. So S goes to, well, what rule should I apply? The first one. Yeah, there's only one rule to apply. What is the rule corresponding to A that I want to apply? Do I want to apply the epsilon one? No, which one should I apply? The BS one. So A, because the A is always there, BS. And then, actually, let's generate ABA. My bad. Yeah, that's my mistake. I want to apply the same rule again. And then finally, at the very end, I want to apply A goes to epsilon to get ABA. Well, think about what happens on that string in the NFA. What happens? How can I go through the NFA? What happens? What state do we start at? The start state, and then we go A over to the state called capital A, then B back to state S, and then A back to capital A, then I do the epsilon transition to the final state. So there's a correspondence between the variables in the grammar and the states in the NFA, other than the new final state. There's a correspondence between the two. Notice that we restricted the rule types to say you can only generate one character at most, which corresponds to, well, either one character or epsilon in the case if you don't generate anything. Any questions on how and why that this is true, that we can convert from any regular grammar into an NFA? Yeah.
Does the or epsilon always take you to a final state, or is it just for this example?
Yeah, it'll always take you to a final state because think about what happens. We're trying to make transitions in the NFA, which means that they go from a variable to another variable. So for the case of the A to epsilon rule, or the rule A goes to little a, either one of those cases, there's no variable to go to on the right side of the rule. So that means we gotta go to some state because it's an NFA, but we can't go to any of the variable states. And furthermore, we can't generate anything else in the regular grammar because there's no variables left as a result. So we gotta go to a final state. So that's why we made it the final state. Other questions? Oh, so regular grammars have the regular languages then. Oh, what direction did we fail to remember? NFA, yeah, going from an NFA to a regex. Wait a second. What could we do? Let's see. Suppose we have an arbitrary NFA. And I'm just going to draw a simple example to see what's going on. So notice here, I can make a bunch of states final if I wanted to. I can do things like this. Yeah, so let's do that as an example. So notice, the start state is the final one, and there are things leaving the final state. Whereas before, there's nothing leaving this new final state because the computation's done. So how would we actually make a regular grammar for this? Well, let's see. Well, the transitions are okay. If we made a variable for each of the states, then the transitions are okay. Because like, say, for Q0 going to Q1 on the A transition, We can just say, oh, Q0, you can make A followed by a Q1. And I could just have the states of the NFA be variables in the grammar that we're making. So we can just reverse that part. So the transitions are okay. There's nothing wrong with that. Because remember, we can either have a single character or epsilon on each transition. So there's no issue with that. What the issue is the final state. And let's actually make Q2 also final, just to illustrate that many states could be final. What do we do with those states? There's actually a few things we can do. But here's the thing. If I have a state in here, and we just do this conversion, then all of the states are going to be variables in the grammar. So I can't just say, I'm going to make a brand new final state and have everything epsilon over to it, because that state is going to be a variable too. And then we don't know what to do with that. So we might as well just handle it like adults right here. So what do we do about Q0? But notice, suppose we had a string that ended up in Q0, one of the final states. Could we quit the computation right then? If the string was completely red, could we just quit the computation right then if we ended up in Q0? Yeah, we could end right there. So notice for a regular grammar, there's only one variable in existence until we get rid of it. What is one way we can get rid of a variable? So we have a variable existing. I want to make it disappear. What rule should I apply for that? Yeah, the variable goes to epsilon. I'm replacing it by nothing. Wait a second. What should we do with the final states here? Let's add a rule for them to go to epsilon. So what if we added the rule Q0 goes to epsilon as well as Q2 goes to epsilon, along with all of the transition things? Why would this work? So suppose that we wanted to look at the string AB. Well, what does it do in the NFA? What are the transitions we can take to get this accepted in the NFA? Goes from Q0 to Q1 and then back and then stops, right? So let's fill in the other rule, which is Q1 can make B followed by Q0. It's not complete, but this is just enough to what we need to do. What is the derivation in this grammar? What variable should we start with? Q0, because that is the variable we're going to call the start variable, because it's the start state in the NFA. So we start off with Q0. What rule should I apply? The AQ1 guy. So A followed by Q1. And then corresponding to Q1, which rule should we apply? The BQ0 thing. So then we have A, B, Q0. And then for Q0, which rule should we apply? The one that makes Q0 disappear, because I'm after AB. And we've already gotten that. So we want to apply Q0 goes to epsilon. So we get AB as a result. Okay? So for the final states in the NFA, we're going to have those variables go to epsilon. But all of the other states that are not final, we're not going to have that rule available to you. Okay?
I have a question.
Yeah.
I feel like in this example, this epsilon does go to the final state though. So wouldn't Q1 have a epsilon transition too?
Yes, but it's going to another state. So here, great question. So if we have that, if we consider that, that'll be Q1 goes to Q2 directly, because it's from a state to another state. So we better have a rule from a variable to another variable. But then we have the Q2 goes to epsilon rule. So let's actually look at an example string for that. Let's look at A. Well, so we know what's going to happen in the NFA. It's going to go to Q1 reading the A, and then epsilon your way over to Q2 to eventually be accepted. So Q0 derives AQ1, followed by, well, then we'll apply this rule right here to say, well, I'm just going to replace Q1 by Q2. I'm just going to cross it out and then rewrite it as Q2. So then I'm going to have AQ2, and then we'll apply the rule Q2 goes to empty because it's a final state. And then we'll get just a single A. So the transitions will always have a variable on the right side. Whether it has a terminal or not, that depends on the transition. But it'll always have a variable on the right side. The only rules that don't have a variable on the right side are the ones that are final states in the NFA. Because it's just modeling the computation. It goes through and it can quit in that final state if it's read all the input. Any questions about this? I feel like you guys want to just move on to the next thing. Any questions about this? Okay. Let me show you in different grammar. So this is, what I'm about to show you is not a regular grammar for pretty much obvious reasons going to be going forward. So let's look at this grammar. S goes to, so how did I do it? Let's see, 0A or epsilon, and A makes S1, I think. Yeah, that's what I want. So this is not a regular grammar. Why?
Both sides.
Yeah, because there's a terminal on both sides of the variable. Fine. What is the language of this grammar? What strings can it make? Well, let's see. And where S is the start variable. What strings could it make? Let's see. Could it make the empty string? Yeah, just do the S to epsilon rule. So epsilon's in there. Oh, so what if we applied the other rule? What string would we get? What is the next longest string that we get? 0, 1. Okay, cool. Now what? What if we did the 0A loop twice? So we did 0A, then went down to S1, then 0A, S1, then epsilon. What string are we going to get? 0, 0, 1, 1. You notice a pattern?
Same number too.
Same, well, almost. It's the same number of zeros as ones, but the zeros are in front of the ones. So in fact, this language is 0 to the n, 1 to the n, where n is at least 0. Well, here's the thing. We didn't do anything with this language, but can you tell me whether or not it's regular? Is this thing actually regular? No. So it turns out to be not regular. What string should I pick to use with the pumping lemma, for example? 0 to the P, 1 to the P. That was the same string we used for the strings that could have zeros and ones anywhere, but the same number. Well, notice what happened. We had 0 to the P, 1 to the P. We pumped in the 0 part. We added more zeros. And then we got an imbalance of the number of zeros and ones. But wouldn't that string leave this language too? Yeah, because look, this is the same number of zeros and ones, but the zeros are in front. So this is not regular either. So by this very simple modification, we can get non-regularity. Isn't that really weird? That you could just make a very slight change to one of the types of rules that you're allowed to have, and we can get non-regular languages. Well, what's stopping us now? What if we can just say, oh, put anything on the right side you want. Instead of just a single variable, single terminal, or epsilon, you can put a whole smattering of variables or terminals, anything you want. That's actually one of the things we do in mathematics. We try to generalize things in a way that makes sense. So by putting anything you want on the right side, that gives us unrestricted freedom as to what we want to generate. And it would cover this case. So let's actually talk about this type of grammar. So, well, what happens? We're still going to require you to have a single variable on the left side, but you can have anything you want on the right side. So think about what happens. Suppose we're in the middle of a derivation here, and there is a variable a that we want to replace by something else, apply a rule to it. Does it matter here what is existing on the left and right of that variable? Does it matter? No, because we are still replacing one variable by a bunch of stuff. So this is actually called a context-free grammar, or a CFG. Oops. CFG. So a context-free grammar then is like a regular grammar, but the rules can have anything on the right-hand side. So we can put two variables on the right side, then pick one to apply a rule to it, and then at some time later pick the other variable and apply a rule to it. So it's not the case that we're going to always have one variable and then at some point later we're going to have 0. We start at 1 always, but we could grow in the number of variables, then shrink, and then grow and shrink. We can have a lot of things actually happen. So let's see. So what is a sufficiently complex CFG? So let's look at, say, this one. So let's think about a computer program. Sorry, your compiler. So what is the very first thing your compiler does when it tries to compile your program? What is the very first thing it does? So have you ever encountered this situation? You forgot to put a parenthesis or a curly brace or something, then your compiler immediately complains to you, oh, you forgot a parenthesis or curly brace there. You fix it, and then you have like 100 other errors. How many of you have ever encountered that? So what do you think the compiler does first? It does syntax checks. In fact, what it does is it ignores everything other than things corresponding to either square brackets, curly braces, or parentheses. And it wants to figure out whether they are balanced or not. So in the case of your program, if you forgot one, then you have an excess one on the front that you don't have matching on the back. So if we look at, say, this string, so let's do left parentheses, left, right, right, left, right. So is this a matching set of parentheses? Well, these two are okay. They match. The inner two match with each other. And as a result, these outer two also match with each other. Okay? So for next time, I want you to, what do you think I want you to do? Have a good weekend? No. Yeah. What do you think I want you to try at least? Yeah, make a grammar for this thing. Because it's actually pretty simple. But you actually have to think, what is the base case and what is an inductive case. So I'll see you next week.